Ever feel like your brain just freezes up when you're trying to do? Like even simple math in your head, like at the checkout counter when you're trying to figure out if you have enough cash,
Yeah.
happens to all of us, I think.
It does happen to everyone, yeah.
But what if I told you that there were some secret techniques out there that you can use to make even complicated calculations really fast,
Mm.
all in your head?
Absolutely true.
That's what we're diving into today.
Awesome.
Our source material is this fascinating book called Mathematics Made Simple, using mental calculation tricks.
Cool.
It's packed with methods, and it claims that it can make anyone a mental math whiz.
You know, I was a little skeptical at first,
I was too.
but let me tell you, some of these tricks are very impressive.
Yeah, I mean, I was looking through it and I was like, wow, this is really cool.
Yeah, and what's great about the book is that it focuses on understanding the underlying patterns in math rather than just memorizing formulas.
Yeah. So let's just jump right in.
Let's do it.
So our listener is about to learn some incredibly useful tricks for multiplication. We're going to break them down step by step, and by the end of this episode, you'll be amazed at what your brain can do.
I am always amazed, yeah.
We're going to start with something that seems very simple, but can be surprisingly tricky.
Okay.
Multiplying by 11.
Ah, yes, multiplying by 11. This one is deceptively simple when dealing with smaller numbers.
The book actually gives a really good example of 63 times 11,
Okay.
and it makes it look so easy.
Right.
All you have to do is add the digits of the number being multiplied by 11. So in this case, it's 6 plus 3, which equals 9.
Yep.
And then you just like magically insert that sum right between the original digits. So 63 times 11 becomes 693.
That's right. It is elegant, isn't it? And this works because multiplying by 11 is essentially like shifting the original number over by one place value and then adding it to itself. But as you said, things can get a bit trickier with larger numbers.
That's what I was thinking. Like,
Yeah.
what if the sum of those two digits is something like 12?
Right.
Does the trick still work?
It does. It does. It just requires a little tweaking. Let's take
Yeah.
93 times 11 as an example again.
Okay.
You add the digits 9 plus 3, which gives you 12.
Okay. Now, we can't just squeeze 12 in there between the 9 and the 3, right?
Exactly. You can't. This is where we need a slightly modified approach.
Yeah.
You place the units digit of the sum, which is 2 in this case, between the original digits. So now you have 923.
Okay.
Then you add the tens digit, which is 1 to the first digit of the original number. So 1 plus 9 equals 10, resulting in the final answer of 1023.
So it's almost like we're carrying over that extra one, just like you would in a regular addition.
That's a great way to think about it. It's all about using familiar patterns to make mental calculations easier.
Yeah. Okay, get ready for this one because the next trick in the book completely blew my mind.
Okay.
It's called left to right multiplication.
Okay.
And it feels counterintuitive at first,
Okay.
but then when you see it in action, it makes total sense. It's like you're breaking all the rules of traditional multiplication that we were all taught in school.
I know, right? This one definitely challenges the way we're usually taught to multiply.
Yeah, they use the example of 2,231 times 3.
Okay.
And instead it starts from the rightmost digit like we're taught in school,
Right.
you start from the left.
Interesting.
It's wild. So you do 2 times 3, and then 2 times 3 again, and 3 times 3, and then finally 1 times 3, and that gives you the answer 6,693.
What's really cool about this method is that you can actually start saying the answer aloud as you calculate it. Imagine doing that at a party. People would be so impressed.
I know I'm already planning my next party trick. I can just see it now.
Yeah.
But I'm wondering, like, what happens when one of those individual products, like 2 times 3 is greater than 9?
Right.
How do we handle that carryover situation?
Yeah, that's a great question. And it's where the method gets a bit more challenging, but it still follows a logical pattern. Let's break it down. They use the example of 3,241 times 3.
Okay.
So 3 times 3 is 9, 2 times 3 is 6. So far, so good. Now 4 times 3 is 12. So what do we do with that 12? We keep the units a digit, which is 2, and carry over the tens digit, which is 1 to be added to the previous product. Remember, our previous product was 6. So instead of writing down 6, we now have 7.
What?
Finally, 1 times 3 is 3, giving us the final answer, 9,723.
So again, we're sort of borrowing that carrying over concept from traditional addition to make this work.
Exactly.
Okay.
And the best part is that with a little practice, these steps will become second nature. You won't even have to think about them.
Yeah, it's brilliant. I'm starting to see how all these techniques are interconnected.
Yes.
They're building on each other to make even seemingly complicated calculations doable in your head.
That's the beauty of it.
Okay, are you ready for another game changer?
I'm ready to hit me.
This one is for multiplying teens like 12 times 13. How many times have you stumbled trying to do that in your head?
Oh, I've definitely been there. Trying to juggle those numbers in my mind can be a real struggle.
Yeah, but this trick simplifies it beautifully.
Okay.
Okay, so the book breaks it down into such clear steps.
Mm-hmm.
You start by adding the last digit of the second number to the entire first number.
Okay.
So in our example, that would be 3 from 13 plus 12, which gives us 15.
Okay.
Then you multiply the two end digits, which are 2 and 3, resulting in 6.
Got it.
And for the grand finale, you just stick that 6 onto the end of the 15 from the first step, and boom, you have the answer, 156.
Wow.
I love how this trick turns a potentially messy calculation into just a few easy steps.
Yeah, what's fascinating here is that this technique exploits the fact that we're working with numbers close to 10 that makes the addition and single-digit multiplication much easier to handle mentally.
Right? It's like finding a shortcut through this dense mental jungle.
Yeah.
But it doesn't stop there, because the book then shows how this same trick can be extended to three-digit numbers near 100, like 103 times 102, and even four-digit numbers near 1,000.
Wow.
The pattern holds true, which makes it incredibly versatile.
It all comes down to recognizing and applying these underlying patterns in math. It's like unlocking a secret code.
Yeah, this is seriously empowering.
Yeah.
I'm starting to feel like I could be a human calculator.
Yeah.
But what happens when we step outside the realm of teens into the 20s, 30s, and beyond? Does this teens trick still work?
It does, with a slight twist.
Oh, I love a good twist. Lay it on me.
Let's use 22 times 23 as an example. Just like with the teens trick, we add the last digit of the second number, which is 3, to the entire first number 22. That gives us 25.
Okay, so far so good. Same as the teens trick, but where's the twist?
Here's where things get interesting, because we're dealing with the 20s. We double the 25, resulting in 50.
Ah, I see. So instead of just tacking on the product of the end digits, like before we have this extra doubling step,
Precisely.
it's like we're adjusting for the larger numbers.
Right, and then just like the teens trick, we multiply the end digits 2 times 3, which is 6, and add that to the 50. That gives us our final answer, 506.
So the key is recognizing what base you're working with, whether it's 20s, 30s, or whatever,
Yes.
and then adjusting the multiplication factor accordingly. That makes it so much more adaptable.
Right. And the book even hints that this concept can be stretched to work with other number ranges too, making it an incredibly powerful technique.
I'm loving all of this.
Yeah.
Okay, are you ready for a more visual trick? This one is called rainbow multiplication, and it's super cool.
Ah, yes. This is a fun one. It's especially helpful for visualizing the process of multiplying any two-digit numbers.
Yeah, they use the example of 24 times 12 to kind of demonstrate these rainbow steps.
Okay.
So first you multiply the first digit of each number 2 times 1, which gives you 2. Next, you multiply the first digit of the first number by the second digit of the second number. So 2 times 2, which is 4.
Uh-huh.
Then we reverse it, multiplying the second digit of the first number by the first digit of the second number. That's 4 times 1, which also gives us 4.
Right.
And now here's where the visualization comes in, because we add the results from those last two steps. So 4 plus 4 to get 8. And you can imagine like drawing a rainbow, connecting those digits that you're multiplying, hence the name.
I love it.
And for the final step, you multiply the second digit of each number 4 times 2, which is 8. Putting it all together, you have 288.
This method is great because it breaks down the multiplication into smaller, easier to manage chunks, making it much easier to do mentally.
It also strikes me as a really clever way to illustrate the distributive property in action.
Absolutely.
We're essentially breaking down the numbers and then combining them in a way that makes the calculation much simpler.
That's exactly right. It's a perfect example of how understanding a core mathematical principle can unlock these amazing shortcuts.
I know the book also covers some even more advanced techniques, like multiplying 5-digit numbers by 11 and multiplying by numbers between 11 and 19. We won't delve into those today,
Okay.
but they build upon the principles that we've already learned. It's amazing how much ground we've covered in just this short amount of time.
It's truly remarkable how a few simple techniques can completely change your approach to mental math. And you know, the best part is these skills only get sharper with practice. The more you use them, the more intuitive they become.
It's like building a mental muscle.
It is.
Speaking of building, we're going to take a short break here,
Okay.
but don't go anywhere, because when we come back, we're going to dive into some seriously mind-bending techniques for squaring numbers.
Awesome. Can't wait.
You won't want to miss it.
I'm ready.
Welcome back. I don't know about you, but my mind is already buzzing with all these incredible mental math tricks. I'm ready for more.
Me too. It's amazing how a few simple techniques can unlock so much potential in our brains. We've covered some impressive multiplication shortcuts so far, but now let's shift gears and delve into the world of squaring numbers.
Squaring numbers, that sounds intimidating, but I have a feeling our trusty guide, Mathematics Made Simple, using mental calculation tricks, has some clever techniques up its sleeve for this too, right?
Absolutely, and it starts with a surprisingly simple technique for squaring any two-digit number that ends in 5. I remember learning this one years ago, and it's stuck with me ever since. It's so elegant.
Okay, I'm all ears, two-digit numbers ending in 5. What's the secret?
Let's take 35 squared as an example. The trick is to first multiply the tens digit, which is 3 in this case, by the next consecutive whole number, which is 4. So 3 times 4 gives us 12.
Got it. 12. What's the next step?
Then you simply tack on 25 to the end of that product, so 12 becomes 1225, which is, believe it or not, the square of 35.
Wow, that's incredibly easy. I can't believe I've never seen this before. It's like a magic trick.
It does feel a bit like magic, doesn't it? And it works for any two-digit number ending in 5. Try it with 75 squared. What do you get?
Okay, let's see. 7 times 8 is 56. Tack on 25. That's 5625. Amazing. It really works. But I have to ask, why does this work? It seems so random.
It's not random at all. There's a beautiful mathematical reason behind it. It all boils down to recognizing patterns. Any two-digit number ending in 5 can be expressed as 10n plus 5, where n represents the tens digit.
Okay, I'm following so far.
Now, when you square that expression, 10n plus 5, get 100n times n plus 1 plus 25. That's the mathematical basis for this trick. We're essentially just taking a shortcut through that calculation.
Wow, it's amazing how understanding the underlying math makes these tricks even more impressive. It's not just about memorization, it's about understanding the elegance of how numbers work.
Exactly. It's like unlocking a secret code that reveals the hidden patterns in math.
Okay, so we've conquered squaring two-digit numbers ending in 5. That was pretty painless. But what about squaring other two-digit numbers? Does the book have any tricks for those two, ones that don't end in 5? I mean,
It does, and this is where things get even more interesting. The next technique involves using a base number and working with differences.
a base number and differences. Okay, I'm intrigued. Tell me more.
Let's say we want to square 83. We can choose a nearby base number that's easy to square mentally, like 80.
So we're basically working with the difference between 83 and 80, which is 3.
Precisely. First, we square the base number 80 squared, which is 6,400. Then we add the difference 3 to the original number 83, giving us 86.
Okay, I'm with you. So now we have 6,486. What do we do with those two numbers?
We multiply them together, 6,400 times 86. Don't worry, you don't need to do that giant multiplication in your head. We'll use another trick for that later. But for now, trust me, it equals 550,400.
Whoa. Okay, that's a big number. But wait, is that our final answer?
Not quite. We need one more step. We add the square of the difference. Remember, our difference was 3 to that product. So 3 squared is 9. And 550,400 plus 9 gives us 550,409, which is the square of 83.
That's incredible. It's a multi-step process. But each step is pretty manageable on its own, making it feasible to do mentally.
Exactly. And the beauty of this technique is that you can choose different base numbers depending on what's easiest for you.
So if I was squaring, say, 47, I could use 50 as my base number.
You absolutely could. You'd be working with a difference of 3 again. You'd square the base number 50 to get 2,500, add 3 to 47 to get 50, multiply those together to get 125,000, and then add the square of the difference 9 to get your final answer of 125,009.
This is seriously mind-blowing. I never realized there were so many clever shortcuts for squaring numbers. I'm starting to see math in a whole new light.
And we're just scratching the surface. The book goes even deeper, exploring techniques for squaring three-digit numbers and beyond. But for now, let's move on to some other fascinating multiplication tricks. We'll get to those larger numbers soon.
Sounds good to me.
Me.
I'm ready for whatever mental gymnastics this book throws at us next. Our listeners are probably eager to learn more too. Welcome back to the deep dive. My brain is doing mental backflips after all those squaring techniques we just learned. It's amazing how a few simple tricks can make such a difference.
It's like we've been training our minds for a mental math marathon, isn't it? We've covered so much ground from multiplication shortcuts to squaring secrets, but we're not done yet.
That's right. We're about to tackle what I used to think was a mental math. Mount Everest multiplying by 11, but this time with 5-digit numbers.
This is where those seemingly basic tricks we've learned really show their power. Imagine being able to multiply a number like 21,342 by 11 all in your head. That's bound to impress anyone.
I can already see myself showing off at parties. So tell me, how does this mental magic work? What's the secret to conquering 5-digit numbers?
Well, the book uses that exact example, 21,342 times 11, to illustrate the technique, and it actually builds on the pattern we saw earlier with multiplying smaller numbers. By 11, we start by writing down the first digit of the number, which is 2 in this case.
Okay, 2. Easy enough. What's next?
Then you add the first and second digits, 2 plus 1, which gives you 3. Write that down next to the 2.
So we have 23 so far. This is reminding me of that trick for 2-digit numbers multiplied by 11, just expanded.
You got it. You're catching on quickly. Now you add the second and third digits, 1 plus 3, which gives you 4. Write that down, then add the third and fourth digits, 3 plus 4, resulting in 7, and finally add the fourth and fifth digits, 4 plus 2, giving you 6.
Wow. So we had 23,476. It's like building the answer piece by piece. Are we done?
Almost. Just tack on the last digit of the original number, which is 2 to the end of that sequence, and there you have it, 234,762.
It's like a mental math dance, moving from digit to digit, adding them up and building the answer as you go. Who knew multiplying by 11 could be so rhythmic?
It is quite elegant, isn't it? And once you practice it a few times, it becomes remarkably intuitive. You'll be multiplying 5-digit numbers by 11 in your sleep.
I'm starting to feel like there's no number I can't conquer. Okay, I'm ready for one final challenge before we wrap up. How about multiplying a large number by a number between 11 and 19? It always seemed so daunting to me.
Not with the right approach. The book tackles this head-on using 1,321 times 13 as an example. It's similar to the 5-digit by 11 trick, but with an added layer of multiplication ready to give it a try.
But I get on.
All right, let's start by writing down the first digit of the number being multiplied, which is 1.
Okay, 1, what's the next move?
Now we multiply that first digit by the units digit of the multiplier, which is 3 from the 13. So 1 times 3 is 3. We add that to the second digit of the number being multiplied, which is also 3. So 3 plus 3 gives us 6. Write that down next to the 1.
All right, so we have 16 so far. I'm following along.
Great. Now we multiply the second digit, 3, by the units digit of the multiplier, which is still 3. That gives us 9. We add that to the third digit of the number being multiplied, which is 2, giving us 11.
Hold on, now we have a 2-digit number. What do we do with that?
Just like before, we write down the units digit, which is 1, and carry over the tens digit, which is 1, to the next step. So our sequence is now 1,611.
Okay, that makes sense. It's like a little mental carryover dance. What happens next?
We multiply the third digit, 2, by the units digit of the multiplier, 3, giving us 6. Then we add that to the fourth digit of the number being multiplied, which is 1. And don't forget to add the carried over 1 as well. That gives us a total of 8. Write down the 8, and our sequence is now 1,618.
We're almost there. What's the final step?
We multiply the last digit of our number 1 by the units digit of the multiplier, 3 giving us 3. Write that down at the end. And you have the final answer, 17,173.
Wow, that was quite the mental workout, but we did it. I can't believe we just multiplied 1,321 by 13 in our heads. This book has truly opened my eyes to a whole new world of mental math possibilities.
And think of how much faster and more confident you'll be with everyday calculations. You'll never be intimidated by a checkout line again.
That's for sure. This deep dive has been an incredible journey. I feel like I've unlocked a secret superpower. But if our listeners are ready to truly master these techniques and explore even more mental math marvels, I highly recommend checking out Mathematics Made Simple using mental calculation tricks. It's a game changer. You can find a link to purchase the book on Amazon in the description of this episode. And for those of you who would like to support our team and help us continue creating these deep dives, we have the donation link in the description as well. We're so grateful for your support.
Thank you for joining us on this fascinating exploration of mental math. Remember, the key is to keep practicing and have fun with it. You'll be amazed at what your mind can achieve.
That's right. Keep those mental muscles flexed, and we'll see you in our next deep dive.